In this video, we'll cover kinetics, the study of reaction rates. Rate expression refers to the mathematical representation of the rate of a reaction return in terms of a reactant or product concentration. So we can see rate expression is the change in concentration. So X final, the concentration, the brackets represent concentration final minus concentration initial divided by time. And we can see that the unit of it is molarity over seconds, or moles per liter divided by seconds. We can see that reactants decrease over time and products increase over time. This is because reactants are used to make products. So when writing the rate of reaction for reactants, the change in concentration of reactants is negative over the change in time. And for the products, the change of rate of change for the rate of concentration changing for products is positive divided by time. To get the rate of reaction, we multiply each term by the reciprocal of its stoichiometric coefficient. So, for instance, if this is the stoichiometric coefficient, then we would use for the reactants minus 1 over A times the change in concentration of capital A divided by T. And for B, because it's a product, 1 over B divided by the change in concentration of capital B divided by change in time. To measure rates, we use this by finding the rates from the slope of a tangent line at a particular point on the curve. We can do this in 3 ways. Average rate refers to just the slope. So we find two points on the curve, so like here and here. The red curve represents the reactance curve, and that's what we're using. So 2 points from here to here, and we find the average or the slope, so y1 minus y2, and then we multiply by the inverse stoichiometric coefficient to get the reaction rate. The instantaneous reaction rate refers to finding the tangent, meaning drawing a line at one point, and then finding 2 points on that tangent, not on the curve, but on the tangent curve, and then multiplying that by the inverse stoichiometric coefficient. Lastly, the last one is the initial rate. So we find the slope of the tangent line when x is equal to 0 at 0 seconds. And then we use 2 points to get the slope, and then we multiply by the inverse of the stoichiometric coefficient to find the rate for the reaction. There are a few factors that affect the reaction rate. One of them is the chemical nature of the reacting substance. For instance, some things just naturally react faster than others. Physical state of the reactants also matters. So, liquids and gases react best because they have low intermolecular forces, they collide more often. Homogeneous reaction refers to some phases that are rapid, meaning that everything has the same state. So for instance, everything is a liquid or everything is gas, and since they have the same phase, the reaction is rapid. When you have heterogeneous phases, for instance, solid and a gas, the reaction doesn't interact well because they can only interact in the interface. So when the interface increases, meaning when the surface area increases, the reaction increases. But overall, it's less than the reaction rate for a homogeneous reaction. Temperature, generally, as the temperature increases, the reaction gets faster. When the concentration of reactants generally increases, the reaction gets faster. And with a catalyst, the reaction gets faster. Rate laws refers to the mathematical expression that describes the relationship between rate and the concentration of its reactants. So for instance, we have here this reaction, and we can write the rate law. We use reactants and basically write K times the concentration of A raised to the power of M times the concentration of B raised to the power of N. K is the rate constant, and A and B are the molar concentration. The reaction order meaning M and N, the exponents, are experimentally determined, and they cannot be determined by anything else. When writing, use only reactants and M, N, and P for variables such as this, or X, Y, and Z for the exponent. Exponents M and M specify the order of the reaction with respect to each reactant. For instance, if M or N add to 1, or if the if either of them is 1, then it's first order. If they're 2, then it's second order. And if they're 3, it's third order. If it's 0, then it could also be 0 order. And the 0 order does not affect rate and is not written in the rate law equation. Again, it could be m or n. And to get the overall order of the reaction, we add m or n, or other variables that exist for the reactants. And the sum over the order of each reactance is the rate law. So rate law is, here we can see 0 order as just being rate is equal to k. For the first order, we can have a and b raised to the power of nothing, but just by themselves. And the sum of the exponents is equal to 1. Here we can see a squared to 2, where the sum of the exponents is 2, or b squared to 2, where the sum of the exponents again is 2, or a with the power of 1 and b to the power of 1, which also sums to 2, and this is second order. Here we can see the same pattern with a to the power of 3, which sums to 3, b to the power of 3 sums to 3, or a to the power of 2 plus b to the power of 1, or a to the power of 1 plus b to the power of 2, which all add up to the third order of exponents. Lastly, we should be able to manipulate K rate and the concentration of the reactants to find other variables. This is expected of us for the problems. Units of K to determine we can use the units of K, meaning, so K is generally in moles per seconds, but we can use the units of it to determine which order it is by using what the units of the rate are and what the concentration units are. For instance, for the rate, we know that the unit for K, or for the rate, is molarity per second, as I mentioned before. For rate, meaning molarity per second, divided by concentration, meaning 1 over m, or multiplied by 1 over m, its reciprocal, is seconds by itself. Here we can see again, if it's rate, or if it's a second order, then it's rate m over s times m squared, and we can see that m in the numerator cancels out, and we have m and s in the denominator, or m to the negative power of 1 and s to the negative power of 1. In the third order, we have rate times concentration divided by the concentration cubed. Here we can see, and this results in, again, the m in the numerator canceling out and m squared being in the denominator along with the seconds. Same thing happens here, where m to the power m cubed in the denominator times seconds. One way to remember this is basically that whatever the order is, m less than 1 is raised to that power. So for instance, m raised to the power of negative 2 or raised to the power of 2 in the denominator is third order. Here, how to determine the exponents and rate law. If we're given the experimental values in a table, we select 2 experimental rates that differ only in the concentration of one reactant, so we can eliminate the second reactant and solve for the change that it would produce in K. So we set up the ratio of the 2 rates and rate laws. We cancel the terms that are equal, and then we solve for the order. When we're solving for the orders, such as if we have 2 to the power of m is equal to 4, we cannot use log with any base. So here, when the base should be 2, we cannot really solve for it. So we do log of 2 and log of 4 and divide log 4 divided by log 2 to get what m is. Finding rate law and rate constant K. To use this, we first have to determine the rate law equation. For instance, if it's this, then we would have that. And use any experimental values to solve for K. So for K is rate divided by a squared from this, and we would use the experimental values, plug those in to find K. The shortcut to determine rate law is that we should know that the relationship between order of reaction and the change in concentration and rate. As A goes to product, if it's zero reaction, no matter what happens to A, the reaction will not change because A is not even in the reaction. So there is no change. And if the value of the rate law stays constant, then we know that it has to be zero order. First order reaction, if anything happens to K, is reciprocated in the rate. For instance, if A is doubled, then the rate is doubled. And if A is tripled, then the rate is tripled. And so on and so forth. For the second order reaction, if A is doubled, then we know that square root of 2 applies to 2, and the rate is 4 times, and it's raised to the exponent of 2. If rate is tripled, 3 squared is 9, so the rate is multiplied by 9. Again, if the concentration is quadrupled, it is 4 squared, which is 16, so the rate is multiplied by 16. We can use this to come up with a shortcut when determining exponents and rate laws. So when if we want to see what happens to the concentration NO, we can find somewhere where the concentration of O is constant. We see that NO is doubled, but that the initial rate is 4 times, meaning that it has to be second order. We can also see this for oxygen. When the rate of NO is constant, we see that as O2 is tripled, the initial rates are also tripled. So we know that it has to be first order. We can use this process to simplify calculating rate law. To connect the concentration and time, we have to use integrated rate law and relate the concentration of reactants and time based on the order of the this is based on the order of the reaction. For instance, if the reaction is 0 order, first order, second order, we have different equations as listed here. Here we can see that A0 is the initial concentration. The concentration at time t is here AT, and K is the rate constant and T is time. Time can be in any units. It does not have a standardized unit, and so is the amount. It can be in any units as long as it's consistent. Okay, linear form of integrated rate law. Here we can see that for 0 order integrated rate law, the equation tells us that the slope is minus k and that the y-intercept is A0. Here we can see, from here we can see this clearly. This is the y-intercept, this is the slope, and that it is a straight line. We know that we can determine the order from the integrated rate law by determining whether the relationship is a straight line or not. If it's not a straight line, then it means that that order does not fit. For the first order, we can see that the slope is ln of A0 and the slope is minus k and the y-intercept is ln of A0. Here we can see that the x variable for all of these is time, but the y variable changes based on the changes here. So here for the second order, we can get 1 over concentration of A as it changes with time. And we can see that here the slope is positive k and the y-intercept is 1 over A0. The half-life of reaction also depends on the order. For 0 order, we have this equation. For first order, we have this, and second order, we have this. We can simplify these equations to get this. And this tells us the half-life of each of these using those equations. These equations are provided on the exam, so there's no need to memorize them. The faster reactions have larger rate constants and shorter half-lives. This makes sense because as reactions proceed faster, it takes less time to reach half the initial concentration. Collision theory is a theory that we use to identify rate law. So models that emphasize energy and orientation of molecular collision to explain and predict kinetics. So the rate of a reaction is proportional to the reactant collision. So the more they collide, the more reactions that happen. Molecules must be oriented properly when they collide. Collisions must have a minimum kinetic energy for successful reactions. So relating to the second one, molecules must be oriented correctly. So the larger the orientation factor, the easier it is for something to orient. For instance, if it's just nitrogen and oxygen, then it doesn't matter if they collide this way or any other way because they have a large orientation factor. Their orientation does not matter as much. Activation energy must have this one, where it is the minimum kinetic energy for successful reaction. We can see in this one that there isn't enough kinetic energy, so the reaction is not able to get over this hump of the activation or energy required. Here we can see this reaction does have enough activation energy, and it is able to complete the reaction as possible. The minimum energy, activation energy, is the minimum energy required to form a product during a collision between reactants. And we can also see how these diagrams, reaction energy diagrams, can be used to show endothermic and exothermic reaction. When reading this, what we can see is that here, this is the energy, and the energy is a lot less, meaning the energy went outside, so the reaction is exothermic. here we can see the same thing, where we start with this much energy, but we end up with this much. So this much energy is gained, and that is an endothermic reaction. We want to go over the Arrhenius energy equation, which is a mathematical energy between the rate constant and activation energy of a reaction. So we have K is equal to, again, the equation here, and we develop this. So K is equal to the frequency factor times the activation energy over R, which is 8.312, times temperature in kelvins. So frequency of collisions is determined by this, and their orientation is determined by this. So as the correct orientation and frequency increases, K increases and the rate increases. Here we can also see this E over activation energy divided by R times T is the fraction of the collisions that happen with enough energy to overcome the activation barriers. So as the energy for this increases, meaning more energy is required to complete the reaction, then there's a lower K and there's a lower rate overall, meaning less of the reaction is happening. If the energy is low, that means there's a higher K and there's a higher rate, meaning more of the reaction is happening. Here we can see there is a graphical determination of this, with ln of K being minus activation energy divided by R times 1 over T plus ln of A. This is called the Arrhenius plot, and this is when K and T are measured with experiments. We can see 1 over T and then ln of K, and the slope is, again, as determined from here, minus EA over R and ln of A. We do not have to memorize this for the test. Okay. The reaction mechanism provides details regarding the precise step-by-step process by which reaction occurs, and each step is an elementary mechanism, which means the actual reaction between the reactant molecules. Molecularity refers to the number of reactants of species in the elementary step. So if there's one species or one reactant, it is one species and unimolecular. A plus B, here we have two species, and it could be same or different, so it could be 2A, and it is bimolecular. We have A plus B plus C, it is 3 species and termolecular. Basically, it's the number of molecules that are required for the reaction. Rate law is determined directly from an elementary reaction. For instance, if we want to determine the elementary reaction, we can just use the coefficient of reactants in a balanced chemical equation. So 2A would result to A squared. Previously, we were not able to do this, but we are able to do it with elementary reactions. So here this table basically illustrates this thing, where A leads to products, overall order is 1. Here we can see 2A, so we see K times A squared is a rate law, and it is bimolecular. Here we see A plus B leads to product, so we can see how A times B is bimolecular and leads to product. We can see the same thing with the termolecular, with A plus B plus C leads to K times A, B, C. Here we can see 2A, so A is squared, because that is the stoichiometric coefficients, and B times K, and that is termolecular. And same thing with 3A, this is termolecular, but A is cubed. And this, again, only applies to elementary reactions. For other rate laws, we cannot determine them without experiments. To determine if the reaction is elementary, we compare the experimental rate law, which will be given to us, with the one that we determined from the balanced chemical equation. So we would write this, and then we would match it with this to see if it works. For multi-reactions, elementary steps must add up to give the overall reaction. Intermediates are products in one step that are just consumed in another, meaning that they don't appear in the reaction in the end. They're just somewhere in the middle, they're used up. Rate determining step is the step that occurs much more slowly than other steps, and the rate of reaction is dependent on the slowest step in the reaction. Basically, an example of this was these two lanes and then one small lane. So how fast you go home depends not on how big these are, but how small this lane is. That is determining how things move. So when using elementary reaction, rate law is determined by the elementary reaction of the slowest step. And we get the elementary reaction again from the balanced chemical equation. And we validate a mechanism such as those by seeing that the elementary steps add up to the overall reaction. And then the slowest step leads to the rate law, and elementary steps have an order of 3 or less. Order of 3 or less is very important. We must also verify this to see that the rate law matches up with the experiments and the elementary steps match with the experiments. A catalyst is a substance that increases the rate of a chemical reaction but isn't consumed by the reaction. So what a catalyst does is it provides an alternate mechanism where the amount of energy is lower to get through the threshold. And so this means that K increases and the reaction rate consequently increases. So catalysts basically speed up a reaction by providing an alternate mechanism. Homogeneous catalysts exist in the same phase as the reactants, and heterogeneous catalysts exist in different phases than the reactants. To identify intermediates and catalysts, we know that intermediates are formed in an early step and used in a later step. So we would first see them in the products, and then they would get used up in the reactants. So they are formed and then used up. They're in products. Catalysts are used up in an early step and regenerated in a later step. So catalysts are basically in the reactants. They aren't made, they're present, and then they get used up and then regenerate themselves in the products. They aren't completely used up, but they cancel out in the end. That is all for this chapter.